Hello everyone. In this video, we will learn to derive the rate law of a given chemical reaction from the initial rates at different concentrations of reactants. There are two different methods to determine the rate law of a given reaction. One is using initial rates, and the second one is using integrated rate law. We are going to learn the first method in this video, that is, determining the rate law from initial rates. First, let us recall what initial rate of a reaction means. The instantaneous reaction rate at time t is equals to 0 seconds is called as the initial rate of the reaction. Let us say we want to determine the initial rate of the following equation. 2 moles of nitrogen dioxide decompose to form 2 moles of nitric oxide and 1 mole of oxygen gas. What we do is we go to the lab and start this reaction and measure the concentration of NO2, which is the reactant of the reaction, at various time points. Let us say the following is the data collected in the lab. We have concentrations of reactants and products at various time points. Next, we plot the concentration of NO2 on y-axis and time on x-axis. Then, we draw a tangent to the curve at time t is equals to 0 seconds. The slope of the line gives us the initial rate of disappearance of NO2. From that, we can calculate the initial rate of the reaction using stoichiometry. This method involves drawing a tangent to the curve, which obviously takes a lot of time. In exams or in the lab, you may want to find the initial rate quickly without having to draw the graph and then the tangent. What we can do is we can find the average rate of the reaction in the first smallest time interval given. In this case, the first smallest time interval is the first 100 seconds. The average reaction rate in the first 100 seconds is equal to minus half change in concentration of NO2 divided by change in time. That is, the concentration of NO2 at 100 seconds, which is 0.0065 molar, minus concentration of NO2 at 0 seconds, which is 0.01 molar, divided by 100 seconds, minus 0 seconds. If we do the math, we get this following number, and the units again are molar per second. The average reaction rate in the first 100 seconds will be smaller than the instantaneous rate at t is equals to 0 seconds, because the rate of the reaction is maximum at time t is equals to 0 second, and it keeps decreasing over time. However, the average rate in the first time interval is a good approximation for the initial instantaneous rate. Now that we recalled how to calculate the initial rate of a reaction, let us now learn how to determine the rate law of a given chemical reaction from the initial rates. We are again going to use the same equation. 2 moles of NO2 gas decompose to form 2 moles of NO gas and 1 mole of oxygen gas. And we are going to determine the rate law of this reaction using the initial rates. The general form of the rate law for the above chemical reaction is rate is equals to some constant K times the concentration of the reactant, which is NO2, raised to the power of its order let's assume as n. The idea is to perform several different experiments with different starting concentrations of NO2 and measure the initial rates of the reaction at these concentrations. For each experiment we conducted, we have initial concentration of NO2 and the associated initial rate at that concentration. If we look at the rate law, we have four different terms: rate, rate constant K, concentration of NO2, and the order with respect to NO2, which is N. We get the values of the rate of the reaction and concentration of NO2 from the experimental data, and we need to calculate the values of K and N. That is, we have two different variables to be solved. Therefore, we need two equations to solve it, which means we need to do at least two different experiments. Let us say we have done two experiments, and here is the data for that. For each of the experiments, I have the initial concentration of NO2 and corresponding initial rate. Next, let us plug in the initial rate and the concentration of NO2 for experiment 1 in the general form of the rate law. The general form of the rate law is rate is equals to K times concentration of NO2 to the power n. For experiment 1, the rate is 1.75 times 10 to the minus 5 molar per second, and the concentration of NO2 is 0.01 molar. Let us call this equation number 1. Next, let us plug in the initial rate and the concentration of NO2 for the experiment 2 into the general form of the rate law. For experiment 2, the rate is 4.5 times 10 to the minus 6 molar per second, and the concentration of NO2 is 0.005 molar. Let us call this equation 2. Now we have two equations and two variables to solve. Let us divide one of the equations with other. Mathematically, it would be easier if we put the equation with the biggest rate in the numerator. In this case, equation 1 has higher rate. Therefore, dividing equation 1 with equation 2, we get the following. K and K gets cancelled, and if we do the math, we get 3.99 is equals to 2 to the power of n, and n is equals to 2. So, the order of the reaction with respect to nitrogen dioxide is 2. Next, we need to calculate the rate constant. Let us plug in the value of n into equation 1 or 2 and solve for K. Let me do that for equation 1. 1.75 times 10 to the minus 5 molar per second is equal to K times 0.01 molar square. If we do the math, we get K is equals to 1.75 times 10 to the minus 1 per molar per second. The units of the rate constant for a second order reaction are per molar per second. Note that the units of the rate constant depend on the order of the reaction. That is, different orders means different units. So, let us now write the rate law of the following equation. The general form of the rate law is rate is equals to K times concentration of NO2 raised to the power of n. We have already determined the values of K and n. Let us plug them into the main equation. This is the rate law for the reaction. The rate law is a very important piece of information for any chemical reaction. Let us say if a scientist wants the reaction to proceed at a certain rate, he or she can plug in the value of the desired rate and calculate the concentration of NO2 required to achieve that rate. Conversely, if we have the initial concentration of NO2, we can calculate the initial rate at which the reaction starts. In the previous slide, we learned how to derive the rate law for a reaction with only one reactant. Now, let us learn how to determine the rate law if we have multiple reactants. Let us consider the following reaction. Carbon monoxide gas reacts with nitrogen dioxide gas to form carbon dioxide gas and nitrogen monoxide gas. The general form of the rate law for this reaction can be written as rate is equals to some constant K times carbon monoxide to the power of m times the concentration of NO2 to the power n, where K is the rate constant, m is the order with respect to carbon monoxide, n is the order with respect to NO2. If we look at the rate law, we now have three different variables to solve: K, m, and n. So, we need at least three different equations to solve for these three variables, which means we need to do at least three different experiments. The following is the data that we collect in the lab. As you can see, we have performed three different experiments, and we have the initial concentrations of carbon monoxide and nitrogen dioxide and the corresponding initial rate for each of these experiments. Since we have control over the initial concentrations of the reactants, we can pick the initial concentrations to make our calculations as easy as possible. When we design the experiments, what we do is we keep one of the concentrations of the reactants constant and they change the concentration of the other reactant and determine the rate. For example, if we look at experiments 1 and 2, the concentration of carbon monoxide is kept constant while the concentration of NO2 is changed. Since the concentration of carbon monoxide is kept constant between these two experiments, the change in the rate of the reaction between the experiment 1 and 2 is solely because of the increase in concentration of NO2. If we look a little deeper, we increased the concentration of NO2 by 2 times, and the initial rate also increased by 2 times. From what we have discussed earlier, we can say that the reaction is first order with respect to NO2. We can also calculate this mathematically. If we substitute the values of concentrations and rate from experiment 1 into the general form of the rate law, we get 1.7 times 10 to the minus 8 molar per hour is equal to K times 5.10 times 10 to the minus 4 raised to the power m times 1.8 times 10 to the minus 5 raised to the power n. Let us call this equation 1. Next, let us substitute the values of concentrations and rate from experiment 2 into the general form of the rate law. The rate for experiment 2 is 3.4 times 10 to the minus 8 molar per hour. The concentration of carbon monoxide is 5.10 times 10 to the minus 4 and the concentration of NO2 is 3.60 times 10 to the minus 5. Let us call this equation 2. Let us now divide equation 2 with equation 1. As we can see, the K and K gets cancelled, and the concentration of CO to the power m also gets cancelled. And we are left with only one variable, which is N, and one reaction. If we do the math, we get N is equals to 1. So, when doing the experiments, if we haven't kept the concentration of carbon monoxide constant, we would end up with two variables, M and N, and only one equation, which is very difficult to solve. Next, let us calculate the value of M, that is, the order with respect to carbon monoxide. If we look at the experiment number 2 and 3, the concentration of NO2 is kept constant, and the concentration of carbon monoxide is changed. Therefore, the change in the rate of the reaction is solely because of the change in the concentration of carbon monoxide. Again, if we look into the data, we increased the concentration of carbon monoxide by 3 times. And what happens to the initial rate? The initial rate also increased by 3 times. Now, what does this mean? This means that the reaction is first order with respect to carbon monoxide. We can also show this mathematically. Let us first write down the general form of the rate law. Rate is equals to K times concentration of CO to the power m and concentration of NO2 to the power n. We already determined the order with respect to NO2, which came out to be 1. Let us plug that value into the rate law. The rate is equals to K times concentration of CO to the power m times concentration of NO2 to the power 1. Next, let us substitute the values of concentrations and rate from experiment 2 into the rate law equation above. For experiment 2, the rate is 3.40 times 10 to the minus 8 molar per hour. The concentration of carbon monoxide is 5.10 times 10 to the minus 4 molar, and concentration of NO2 is 3.6 times 10 to the minus 5 molar. This is the same equation from the previous slide with N value written. Let us again call this equation number 2. Next, let us substitute the values of concentrations and rate from experiment 3. For experiment 3, the rate is 1.02 times 10 to the minus 7 molar per hour. The concentration of carbon monoxide is 1.53 times 10 to the minus 3 molar, and the concentration of NO2 is 3.6 times 10 to the minus 5 molar. Let us call this equation 3 and now divide equation 3 with 2. The K and K gets cancelled. The concentration of NO2 also gets cancelled, and there is only one variable left, which is M, the order with respect to carbon monoxide. If we do the math, we get M is equals to 1. We now have orders with respect to carbon monoxide and NO2. The next step is to determine the rate constant K. To do that, we need to plug in the values of M and N into equations 1 or 2 or 3. You can try to do that. Focus on the units for the K.